All right, the first derivative test is one of the ways we can find local minima and maxima. So we've already seen that you find the global minima and maxima by just checking all the critical points and the endpoints and just looking for the biggest and smallest values. But local minima are a little bit trickier. So one of the ways we can do that is with this first derivative test. So the first derivative test is checking to see if the sign, the positive or negative of the derivative changes on either side of the critical point. If it does, there is a local extrema there. So technically it would be a local extremum. So it could be a minimum, could be a maximum. You'll know based on the sign. So if f prime of x goes negative to positive, well, that's where you've got something that was going down and now going up. So that would be a local minimum. If f prime of x goes from positive to negative, that would be going up, switching, and now going down. So that would be a local max. And if f prime doesn't change, then that would be either the example of it's going up, flattens out, and continues going up, or it's going down, flattens out, continues going down. So that would be neither. It's not a local minima or local maxima. So for the first example, we want to find the local extrema of the function f of x equals x cubed minus 3x squared minus 9x minus 1. So the first derivative is going to be equal to 3x squared minus 6x minus 9, which we can factor to be f prime of x is equal to 3 times x minus 3 times x plus 1. So this means the critical points are at negative 3 and negative 1. Sorry, positive 3 and negative 1. So we need to look at what's happening kind of on either sides of this. So I'm going to evaluate f prime of negative 2, and that's going to give me a positive number. We don't care particularly what positive number it is, we just care that it's positive. So I can do this real quickly by looking at the signs here. So negative 2 plus negative 2 minus 3 will give me a negative number. Negative 2 plus 1 will give me a negative number. Negative times positive is positive. Now we need to check a point between negative 1 and 3, so we're going to check 0. Plugging that in, we get a negative, a positive, and a positive, so that'll be negative. And then check a number on the other side of 3, so let's check, say, 4. And that will be positive, 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 so a positive number. So what we're doing here, if you didn't quite track that, is imagine a number line, and I've got my critical points on it. Negative 1 and 3. So I know that whatever's happening to the left of negative 1, it happens like that for the entire span. What happens between negative 1 and 3 happens the same through the entire span. And what happens after negative 3 is the same for the entire span after that. So what I've done is I've just picked a point at random. So negative 2, because that's easy to work with. 0, because that's easy to work with. 4, because it's a nice whole number. And I see that I have positive derivative behavior, negative derivative behavior, positive derivative behavior. That means my function was increasing, decreasing, increasing again. So that puts negative 1 as a local max. 3 as a local min. So those are my local maxima and minima. And this was just from finding the critical points and then checking all the ranges kind of on either side and in between the critical points. We'll do a second example here. Locate the local extrema for 5 times x to the 1/3 minus x to the 5/3. So the first thing we'll need to do is find the derivatives here. And so you can do that using the power rule like we've seen before. And that will give us, that will give us 5/3 x to the negative 2/3 minus 5/3 x to the negative, not to the negative, just to the positive 2/3. So we got 5x to the negative 2/3 and then 5x to the positive 2/3. Let me just make sure that matches with my notes. Great. And so this can be simplified. I'm not going to go through and worry about going through all the algebra, but you end up with, you can write this in the form of 5 times 1 minus x to the 4/3 over 3x to the 2/3. So you combine that and factor and various other things, you get this. So we know that our critical points are going to be anywhere that this equals 0 or it's undefined. So the critical points would be plus or minus 1 for the numerator equaling 0, because plus 1 to the 4/3 will give 1, minus 1 to the 4/3 will give 1, so 1 minus 1 is 0. That's where we get these. Then we also have 0, because in the denominator, when you plug in 0, you get the whole function being undefined. So that means we've got 3 points here, -1, 0, and 1. You can imagine our number line here. So we need to pick a point that's less than 1, a point between -1 and 0, a point between 0 and 1, and a point greater than 1. So f prime of -2, pick a nice whole number. And if we plug that kind of in and think about it, -2 to the 4/3 is going to be some number smaller than 1. Sorry, some number bigger than 1. So 1 minus that means we're going to get a negative number. On the bottom, it's going to be positive because of the squared. So because of the squared and because of the 4, any negative sign goes away, and it just is 2 to the 4/3 bigger or smaller than 1. It's bigger, so 1 minus a bigger number gives us negative. And on the bottom, it becomes positive, so we just have a positive times a negative divided by a positive, we'll have a negative value. Then if we plug in -1/2, by similar logic, we know that we're going to have the positive 5. We're going to have positive, because 1 minus 1/2 to the 4/3 is going to be a positive number. And on the bottom we'll have positive, so this will be positive. If I plug in the 1/2, we'll get a positive 5, a positive number from the 1 minus 4/3, x to the 4/3, and then a positive denominator. So that means we'll have a positive number here. And then lastly, for f to the 2, for the same reason that f of -2 gave us the values it did, we're going to end up with a negative value here. If you're not sure about the math I did here and kind of the quick eyeballing calculations, check with me in class and we'll go over it, and it'll be a lot easier to walk through it with you in person. So if we went from decreasing to increasing to increasing to decreasing, well, you'll notice here that that means 0 doesn't have a change, so it's not a local minima or a local maxima. So we know that the -1 is our local min, and positive 1 is our local max, or a local max, I should say, and 0 is neither, because it was increasing before and it's increasing after. And if you're curious, the function looks something like this. And so you can see why in the middle here, it's not a local minimum or a local maximum, because it goes vertical basically at that point. And so that's how we use the first derivative test to find local extrema.